Hello folks, this video tutorial is in the series that I'm doing on uh, dynamics analysis of single degree of freedom system with the Catia program. I refer to this thing as the killing a fly with a cannon series because the problem is so simple that there's no reason to want to do it on Catia. However, if one insists, then at least I'll show you the basic process behind creating a mass spring damper system. And it's not straightforward, I can assure you that. The title of this presentation is actually Harmonic Dynamics Response. And specifically, I'm going to be using the white noise modulation to do the program. Now, harmonic dynamic response is another way or a fancy way of referring to a steady state solution or steady state response that you commonly see in the vibrations courses, introductory vibrations courses. And one other motivation behind me doing this series is that students take my vibrations course, they know how to do Catia, they know how to do finite element in Catia, but doing the vibration problems as a single degree of freedom or multi-degree of freedom system was not straightforward and was not described in the help documentation. So the difference between the first two videos that I did and this one, there we used a transient dynamic. That means that the solution that we looked at was displacement of this mass as a function of time. Here, we're going to be doing a harmonic dynamic response, or we're going to find the amplitude of the steady state solution in terms of the frequency or the frequency ratio. Okay, so the horizontal axis is not time, it is the ratio of the driving frequency omega over the natural frequency omega n. And on the right side of it is the phase difference in terms of not time, but in terms of the frequency ratio once again. Okay. Now let's go to the next slide. For the data that's given, the natural frequency comes out to be 0.225 hertz, and the damping ratio is 0.176, which is 17.6%. Okay, so when you look at the vibrations textbooks, you see that the solution of this problem, this is all assuming that steady state doesn't depend on initial conditions, obviously. The solution is of this form. There is an amplitude, big X, and there is a phase, theta. Big X is given by that expression, and incidentally, this F naught that you see up there, although I didn't say it in this particular video, it is actually big F naught divided by K, okay, but divided by M, sorry. This F naught is big F naught divided by M. So the amplitude is given in terms of this expression. Notice that damping plays a role. So the bigger the damping, kind of the smaller the amplitude, you can see that. And the phase also depends on the frequencies omega and omega n and damping. Now, another way of writing this is you see up here, and this is very common. They write things in terms of the frequency ratio and non-dimensionalize it. So if you give me omega, I know omega n, I know r, and I know the damping, I plug it in here, and I will find the amplitude x and the phase angle theta. There is one caveat though. Generally speaking, most textbooks in vibrations assume that this phase angle is between 0 and pi. For example, if they get anything based on the tan inverse that is not in that quadrant, they add pi to it so that it puts it in that quadrant. It looks like, and this graph that comes from, I think, Inman's book is actually using that straightforward convention. Catia's phase plot is actually assuming that the phase is between minus pi and 0, not between 0 and pi, minus pi and 0. So what you see there, when things are plotted, you see that this is all mirrored. Okay, this will all be mirrored, okay? Or I call it flip. Now, these two slides, the next two slides, I've put it in the first two videos because it shows you the basic process behind creating, this mass spring damper system, and I don't go through it, one line by line. But when I do the tutorial, you'll see that actually these are the steps that I'm following. One other thing is that in the previous two videos, I showed you that unfortunately in Catia, in order to do a spring problem like this, you need to create a dummy beam element because otherwise you won't be able to proceed. And I will show you, in fact, today, if I don't create the beam element, what issues I'm going to run into, which means I have to fix it by going and mesh the beam element. The role of that element is totally kind of irrelevant, but you need it in order to be able to access, for example, restraints and clamps and forces and things like that. And unless you create the mesh, the beam mesh, you will not be able to access those icons. Okay. One of the things that the material properties that you put on that beam, it should be so so much altered so that it doesn't affect the stiffness of the beam and the mass that you put at the tip of the beam. In other words, I take, for example, aluminum, put it on that beam, and then the Young's modulus of aluminum, which is 70 gigapascal, I change it to 0.1 so that it has no stiffness effect. That beam has no stiffness effect on the spring element. And the same thing with the mass. So I reduce the mass from 2,700 kilogram per meter cube to 0.1. So basically, it's a massless beam. Okay, so let's go ahead and do that. One other thing is that here I'm going to do this. Notice that I'm assuming that the amplitude F naught, big F naught, right here. I'm assuming that the amplitude big F naught does not depend on omega. It's a constant. That's why I can use a white noise in order to do this. But later on, I'll do a problem where actually amplitude is a factor of frequency, driving frequency also. There we have to create a frequency modulation, just like we did time modulation for the other two, or one of the other two tutorials. Okay, so let's go ahead and do that. I'm going to create a point at 0, 0, 0. This is the wall, the left side of the spring, basically. I'll create another point, which is 1 meter away along the y direction. That's going to be the place where the mass is going to be placed. So this is 1 meter. So create a line between this point and that point. All right. And apply material to it. On this part, I'll make it aluminum. It's totally irrelevant. But I go and change the properties of aluminum to, under the tab, analysis tab, from 70 gigapascal, I put it to 0.1 pascal, which means pretty much nothing. And this is the density. I'll put at 0.1 kilogram per meter cube. Now, it really doesn't matter whether you put aluminum, steel, nickel, whatever. Just make sure you reduce these values so that they don't affect the rest of the problem. Now we're going to go to generative structural analysis. So in the previous two videos, what I did is actually I first meshed this thing and then created my spring element, basically. I want to show you that if you don't mesh it, what will happen. The other thing is that we're going to do this thing in 3 steps. The first step is static analysis. That means that we're going to apply a load of 10, a load of what is that? A load of 10 Newton here. That's a load of 10 Newton here, which I forgot to mention at least in this video. This F naught is 10 Newton, and I'm going to apply a load of 10 Newton. So do a static problem. What I should be getting is 10 Newton divided by the stiffness of the spring, which is 4, and you're going to get 2.5 meters of deflection. And this allows me to debug any issues that I might have. So first we do static analysis. Now, instead of meshing this, I will, I'm going to show you if I don't mesh it, what will happen. Now, remember, after I meshed in the previous two videos, then I created the analysis connection, and then you did the user-defined restraint. So let me go ahead and suppose that I don't mesh this thing right now. I'm going to create the connections, no problem, I can do that. Let me hide these points, by the way. Hide this and hide that. And create a connection. The first component is this. Second component is that. These are identical things that we did before. And then I do a user-defined distant connection. The type I'm going to use rigid spring rigid. You can use rigid spring or you can use spring rigid. It makes no difference. So for the support, the only thing that I can pick is this connection that I created right there. No problem. This is exactly what we did before. The problem comes now that notice that this restraint and the loads are all dimmed. So basically I can't do anything. I created this, but there's nothing much I can do. So now I'm going to go mesh this. So let me hide this connection first of all. Let me hide this. Okay. I want to hide that. Hide it. Oops. All right. Doesn't matter. Let's click on the beam. Notice that when I click on this and mesh it, suddenly these things will light up. So click. See that? So now if I'm having hard time selecting this, I was trying to hide that. Where is my part? My part must be in hiding somewhere. Is it there? I'm having a bad luck with this. So let me see what is, something is hiding here. That line, maybe I can take it from here. Hide and show. Just a second. Okay, mesh it. There, okay. I'm really sorry. I had to select my line. Eventually, I went to the tree and did that. And we say, okay, now you have two choices. Remember, this whole thing is 1 meter long. So I can make, for example, if I say 0.5, it's going to put two elements here. If I say 1, it's going to put one element here. If I say minimal mesh, it just takes that and puts a single element through there. It's entirely up to you how you want to do that. The reason I don't want to, the reason I'm not going to say 0.5 is that when you have 0.5 two elements here, there's more than a single degree of freedom that's going to be created, and I have to make sure that I pick the right one. So that's why I did minimal. Say okay, and in fact you can check that. You go here, you say right-click mesh visualization, and the mesh pops up. And let me hide this thing again. There, you see that? It puts a single element here because I said do a, oh, actually, I don't think it did it. So let me go ahead and delete this. Let me go back there. Minimal mesh. Let me try doing this thing again. So let me delete this. Okay. So let's try to mesh it again. We're going to mesh this line. And minimal mesh, I think we should put one element through that length, but for some reason, activate the mesh. Oh, wait a minute, we got a problem here. You can see that there are duplicate nodes here. Let me do the following. Let me go ahead and delete this. Actually, let me go to the generic connection here from this line and use Yeah, maybe rigid spring. So, okay, so let me go ahead and use the spring rigid or rigid spring. It makes no difference. And then say okay. And now let's look at the mesh. Yeah, okay. So you have to be careful. If you use rigid spring rigid, it puts two elements. If you say rigid and rigid spring or spring rigid, it creates a single element. Now, in the previous two videos, I did not pay attention to this thing. I said either one of them can be used, but I'm not sure. Maybe there I use rigid spring, just like I did right now. Okay? Yeah, it happens. Good. So here's what happened. This I used rigid spring with a minimal mesh, right? Minimal mesh. Remember here, it was minimal mesh. And although it says the size is 0.5, because it said minimal mesh, just put one element through that. Very good. We're done here. Let's deactivate this. I think we wasted some time there. Where is my part? Where is my line? Here's my line. Okay, good. So clamp this end. Okay. And this end, we're going to assume that it moves only in the y direction. Right there. And we apply a load of 10 newtons here. These are identical steps to the previous two videos. 10 newton. Hopefully we didn't forget anything. Although I did forget, it's the cross section of the beam that I did not specify, because if I run it now, it's going to come back and say, you didn't give me the cross section. Let's try it. It's going to come back and say, you didn't give me the cross section. Right here, it says acquisition without property, acquisition failed basically. So okay, leave that. Let's go and apply a beam cross section beam property to this. This radius is irrelevant, so just put a 0.1. Okay, now we're going to run it, and there won't be a problem. You're going to have a deflection of 2.5 meters. There we are, you can see that. There is a deflection of 2.5 meter, and at least for the static one, we are done. You activate. All right, now we're going to insert a frequency case, identical to the previous cases. For the restraint, I use the reference, and the reference is the stuff that I put in the static case, right there, see that? And you select it. And I have to put a mass here, right? A lump mass there. So there's the masses. Click on the first icon, click this corner, and 2 kilograms. And if you zoom in, you see that there is some icon which looks like a lumped mass there, which is okay. Now, we're going to run this thing and run into a problem. You'll see why. And I've mentioned this thing several times before. It says, hey, you're asking me to extract 10 frequencies, but this is a single degree of freedom. So there's only one frequency. That's because when I created the frequency case, I double click on it. It's default 10, asking for 10 frequencies. It's a single degree of freedom system, therefore it has only one frequency. You say, okay, I change it to 1, and we're going to run it. And there won't be a problem. If you want to see what is the frequency extracted, double click, it says 0.225 hertz, which is exactly what we had here, 0.225 hertz. Okay, good. So the frequencies have been extracted. Now we go to insert. If you want to do time variation, it's here. The first two videos are like that. This is harmonic dynamic response, frequency, basically variation. It says, okay, where is the reference frequency extraction, which is right there. See that? This is the one that we just did, right there. And we say, okay. Now, when it comes to expand this thing, first of all, the load. If you click on the load, it says, okay, where is the load that you select? Remember, that is the load that we put in the static case, 10 newtons, right? Right there. But then it says, where is the modulation? Well, I don't have a modulation. I had to create it in the previous two videos, and I have to do exactly the same thing here. Cancel that because we can't proceed anymore. So here's the modulation toolbar. If you have a constant amplitude over all frequencies. We can, a constant amplitude over all frequencies. That's white noise. You click on it, it's going to create a white noise modulation for you, which is in the tree somewhere here. Let's find out. Right there. Right there. And now we go and do that load thingy. So double click on load excitation. Go and select your load from the tree, static load. And for modulation, you select that white noise. And this is a factor that you can scale things by. For example, I put 10 newtons there. If I wanted, hypothetically, if I wanted 100 newton, then I can take that 10, put a scale of 10 here, scale factor of 10, and that turns it automatically. But I don't want to do that. I want to keep it the way it is. So we say, okay. That's pretty much it. So you go here, you go to this, there's nothing to do, you don't run it. You go here, right click, generate 2D plot. We have done this thing. Next, one graph, finish. Now it says, okay, where is that node that you want to display amplitude versus frequency? Well, I have to go here, and from the tree, I have to select that node, okay? That was this node, right? Right there. That's node number, just happened to be node number 3. Add, we say close, and notice that a 2D plot has been generated. Double click on it, and you get this. Which certainly does not make sense, okay? We have to go and fix this. Let me see, something must have happened. So let's go and minimize this. Oh, that was node number 1. Okay, yeah, inadvertently I selected node number 3. Okay, so let's go here to that results. Cancel. Let's get rid of this. Delete. Let's go back here and select the. Now this, I don't want it to be node number 3. I want it to be node number 1, right? It was this one. It won't let me change this. So what I have to do is, let's do the following. Close up. Let me deactivate the default plot. Okay, it's a lot better now. So let's go ahead and double click on this. And go and select node number 1, which is better be node number 1. Yep, node number 1. Because in the previous case, I selected it from the tree, but that was a deformed shape. So I thought what I was picking was this right end. It was actually not that point. Okay, so add, we say okay. Double click on the plot, and this is what we get. Okay, couple of things. Notice that the frequency range is 0 Hertz to 10 Hertz. I don't want to go all the way to 10 Hertz. Maybe I want to go from 0 to 2 Hertz, because remember, the natural frequency was 0.225. This is just an overkill. So no problem. Just close that. Double click on harmonic response. Don't go from 0. Go from 0 to 2 Hertz. 20 steps. We'll see what that thing means. Double click on this again. Sorry, double click on the plot again. That's a lot better. But 20 represents, the reason that it looks like this jagged line is because we didn't use enough stations along the way. So just double click on this thing, but use 200 or 100. It's an overkill, but that's okay. So click on the plot again, 2D plot again. Oh, that's a lot better. You can see that. So it's supposed to be something like this. Now, the thing is that doesn't quite look like that. Let's find out why. What was the value of the damping that we had? The value of the damping that we had, if you click on the damping, notice that by default, it takes 1% damping. Mine is not 1%. Mine is 17.6%. Okay? 17.6%. We say okay, and close this, and double click on that. Notice that it brings it down, right? Right there. You can see that It's not jagged, it brings it down. Now, the other thing is that what if, now obviously I don't have the results to compare with. You can see that, I mean, once you have 17%, which is somewhere, somewhere over here, 17% is somewhere over here, you can go and plot these things, you will see that the numbers match. What about the phase? So we say close, close. Oops, double click, didn't want to close that. I put the cursor on the left-hand side, right click, format. I don't want the, well, I don't want the amplitude. I want the phase in radians, for example, or in degrees. It doesn't matter. It's up to you. So, for example, degrees, and notice that this actually doesn't look like that. It looks like this. And that's because Catia, it seems that they're, by convention, they're using a phase range between minus pi and 0. Okay, so this is the phase. This was the amplitude. Oh, the amplitude right there. This is the amplitude. Now, the other thing is, what if the damping was 0? What if damping was 0? No problem. Double click on damping. Remember, Catia by default puts 1%. I change it to 17% because that's what my problem was. And we say, this thing over there, and run it. Run it. No, don't run it. You already have everything that you want. Results here. Notice that it actually shoots to infinity, kind of shoots to infinity, because without any damping, we know that at that natural frequency, the amplitude becomes infinite, and that is a good indication that it's actually shooting to infinity. Okay? Yeah, so that's pretty much it. So what I'm going to do in the next video tutorial, I will do a problem where the amplitude of the vibration depends on the driving frequency. Now here, I ran into a few issues, and that is, for example, when I was trying to mesh this thing, I couldn't get the line. Eventually, I went there and selected it from the tree, selected the line from the tree, which was easier for me to here to mesh it. And yeah, that's pretty much it. Good luck.